Welcome to this IIoT and Manufacturing Analytics experience. Most of our customers already have connected devices in the factories, whether this is machines, sensors, RFIDs, AVGs, and they use it to have greater visibility throughout the manufacturing process, or of course they use it for the safety of the operators. But all of that data does not necessarily need to be used only for manufacturing life cycles. It can be used for maintenance and real-time operations. Indeed, with that data, you're capable of understanding the actual behavior of each of the machines or each of the systems so that you can actually improve its maintainability and its overall efficiencies. This is what we're going to try to demonstrate today, but I'd like to share with you first some of the challenges that are going along with it. You need to be able to collect, process, store billions of events. You need to be able to handle the variability. So you need to be able to manage the fact that the data is coming from different sources in different formats. You need to be able to handle the velocity, and more importantly, you need to handle the difference in between the velocity speed. Some of the sources provide data with the pace of thousands of parameters every milliseconds, and some other provide the data by batch of few events every 10 seconds. Still, you need to connect them together. So today what we're going to do is we are going to drive you into that process. We will show you how we can connect to the equipment to get all of that data. We will show you how we use that for real-time monitoring and operations. We will then show you how with that data we can do predictive maintenance and failure prediction. We will then show you how we can, from these failures, anticipate the right resolution path, orchestrate it, plan it, and execute it while doing continuous learnings. But first things first. We told you need to have the right data at the right time at the right place. So within 3D Experience platform Delmia Apriso, we actually have the ability to connect directly to the devices. And we are using for that standard communication protocols, OPC, MQTT, Kafka, whatever. When it comes to high throughput data, such as time series, thousands of parameters every milliseconds, we have a partnership with OSIsoft, which have the right connectivity and data infrastructure stacks for handling this type of data. Of course, what matters is that when having connected this data, we need to be able to have a single contextualization environment. So within the 3D Experience platform, we have a single abstraction layer that allows to connect with consistency all of that data. So you can do the proper interpretation, you can do the proper contextualization in a consistent manner over a whole factory. Beyond that data, we are also connected to unstructured information, such as shop finding reports as an example, or ERP data, so that we can do more advanced analytics and typically predictive maintenance. So what we're going to show you today is we're going to show you how we connect to the equipment, both directly to the equipment or through time series through OSIsoft. We will show you how we use that data to do real-time maintenance and operations of the factories. We will show you how we can complement that with additional data, such as unstructured data, to do predictive failures and predictive maintenance. And then we will show you how we execute on that predictive maintenance. Indeed, let's start, if that's okay for you, with real-time maintenance and operations. So if you don't mind, we need to go on that side of the screen. So what you see at the moment is our facilities are running live. And we are currently monitoring 3 machines on that facilities. You can see here live data from these 3 machines. Let's go on to the first one. All of these data are real-time data. Real-time because you want to be capable of providing the right actions in case of unforecasted events. You can still play a time machine. So what you see here is the last 24 hours. But of course we could roll back into the last week or the last month if we wanted to. You have many KPIs and charts which are representing decades of industry knowledge and know-how on how to best operate a factory. As an example here, we're looking at the main reason for failure for that specific machine in the last 24 hours. But real-time operation is not only about the maintenance and the performance, it's also about the operation. So let's see what's happening on this machine as we speak. So currently we have one work order running. We're manufacturing that gearbox for a single object. You actually have the lot number, which will be important for traceability. You will see that later. And you know when this has been scheduled and for what. We also have all of the other work orders that would sit in the queues that will be manufactured next. What matters as well is, as you can see here, you can also see what are all of the components and materials that are going to be used for this specific gearbox. That's very important because here this is how we are rebuilding continuous traceability so that you always know what component is being built into what specific lot. From a single click, by the way, we could have asked for a replenishment. Here, you also have a straight access to the high throughput data, so the millisecond scale parameters, detailed parameters of the machine through OSIsoft. Last but not least, efficiency on the shop floor also requires ability to communicate with extended team. In that case, our agent may want to talk to the support department because he's requiring help. In a single click, he can access to the support people. And by that single click, not only he talk to the support people, but the whole context comes along with it. So in other words, the support agent, whenever he's getting a request, he knows on what machine this agent is currently working. He has access to the right tooling descriptions. He knows what are the work orders that are currently in production, so he can provide the contextual support. And last but not least, of course, you know, from the same screen, we could have launched an inspection if we wanted to. So now I have shown you how we can manage real-time data for performance and operation. What I'd like to show you now is to go to the next steps, which is what can we learn on that data and what can we predict on that data. And if you don't mind, we need to go on the other side for that. So, Christophe, we're going to talk about predictive maintenance. Can you show me some of the potential predictive failures that we can look at? So here we are using all of the data coming not only from a Priso, but also from the real-time machine themselves or from the ERP system. You can see that we have predicted various failures. Some of that, by the way, are normal failures. I know they may look strange. My boss don't like the idea of a failure that could actually be normal. However, the end of life of a tool, it's a normal failure that we could have planned. But the fact that we could have planned doesn't mean we did not decide that we want to still use technology and algorithms to optimize what is the best potential date for changing that tool. And of course, we have abnormal failures, such as abnormal wear on toolings or quality problems. We will come back on these issues later. First, I would like to share with you the type of data that we need to be able to do such predictions. Can you show me the factories? Indeed, you have to know that it is not possible to learn from a single machine. To be able to learn and do prediction, you need both lots of historical data and you also need lots of wideness in terms of data. Here, we are learning on complete factories where we actually have over 60 machines distributed in many centers. I'm going to go, of course, in my Shanghai transmission equipment, where I actually have 6 machines in 4 work centers. Let's go into more details on these machines so you understand. The reason why I get you into that level of details is because I want you to understand the specific nature of the data set that we need to do the learning. Here, on my 6 machines, by the way, I'm monitoring the OEE. You can see that the least performing machine is actually this one on this work center, so we can continue to drill down to identify the machine that currently are the weakest in my whole facilities. Let's go on the machine details. So, let's look at this machine 5X2001. The type of data that we have is a combination for that specific machine of many data sources. Of course, we are connected to the Priso, so we have every events on that machine, whether work orders, scheduled maintenance, issues. Then you also have all of the real-time data. And by the way, you can start to see here some of our prediction. Go down. Then we also have, that's more interesting, what you see in blue here are simulated data. You've heard a lot about the value of combining virtual world and real world. So the blue is coming from the virtual world. We are running simulation of the load spindle. And then we are comparing it with the red, which is actually the real value of the load spindle, so that we can identify deltas. These deltas by itself would not be enough to suggest that there will be a failure. However, this is additional triggers which combined with all of the other data allows to identify risks for failures. So very interesting combination of virtual world and real world here. Let's go back on the predicted failures. So let's see this one first. On the predictive failure, we are doing multiple things. Of course, we are predicting the failure. That's already a big thing. But beyond that, we are also predicting the recommended actions to recover the situation. How do we do that? We have developed a deep learning engine, which is actually doing an automatic comparison in between the predicted failure with past failures. And because we're capable of recognizing past failures that were similar, we are indeed capable of identifying for each of these failures what was the resolution path. Here in this example, for this abnormal behavior of the tooling, there were two different resolution paths, one which was about the provider and the other one was to change the tool path to release the pressure on the tooling. So that's an example. Let's go back on the first one. This one is a simple tool change on our machine 5X2001. Of course, the recommendation is to change the tool. What I suggest is let's send a task to make sure someone gets known that he has to change the tool on this specific machine. And I am quite fortunate because the agent in charge of doing this work is just sitting right on the other side of the table. So let's allocate the task, and I'm sure Sébastien on the other side will receive it. Sébastien, did you receive the request?
Yeah, sure. Hello, so the goal for me now will be to include the maintenance order as it has been predicted and asked by Morgan. So here we are on the production plan of the factory, of the fabrication work centers and machines. So what you see on the left part of the screen are the different machines we have, including the Romy one, which will be the one on which we will have to insert the maintenance order. On the main part of the screen, you are having all the different operations and work of the work orders on the Gantt chart, and if I highlight them, I can see the different steps going through the machine and so through the process. So let's now create dynamically our maintenance order. I will name it MO6, for example, and choose the tool T1 routing, the tool we have to change. We'll do it once, and I will choose a specific color, which will be blue, for example. Now I've created the order. The goal will be to simplify the best time within this production schedule to insert it. So to do this, we might be interested in having information about the advanced delay status of all these work orders, and for that we have this specific color showing that for the moment everything is green, so on time. So let's now insert the maintenance order I've just created. To do this, I can easily drag and drop the order into the production schedule and dynamically and quickly see the impact. So here I can see that I have put multiple work orders late, so not meeting the customer due date anymore because of the new maintenance order that I've added in my schedule. They switch from the green color on time to the yellow one late. So now the aim for me will be to find the best place in my schedule, okay, in order to not disturb as low as possible my current production plan. An additional information that can be displayed here is this specific color I've set earlier to be able to identify quickly which work orders are meant for maintenance. So for example, blue color, or for real customer orders, or real work orders, the gray ones. So now that I have created quickly and inserted to my production plan this maintenance order, I can now just send it to execution so that the people in the shop floor will receive it and will be able to execute.
So I am now the agent in charge of executing that work order. Of course, this screen, I typically have it on my iPad or on my phone. This is my biggest iPad. So here I've received my task MO06, and I actually have to execute it. What's interesting is that what we have decided is to make sure that the execution is made in an effective and in a safe manner in the factory. We are delivering to the agent the guidance and the instruction in 3D, so that the agent will receive all of the step-by-step actions that needs to be conducted, and that will be exactly in the right description of the machine. So 3D as a universal language with no risk of interpretation of the written text. So he knows exactly what he has to do. Not only that, but if he wanted here, he could also put some additional comments in the 3D if he finds anything inconsistent that could then be capitalized into the enterprise knowledge and know-how. What we wanted to show you today, we wanted to show you that we can connect to the equipment. We wanted to show you that because of that, we're capable of doing real-time operations and performance analytics. We wanted to show you that with all of that data, we are capable of doing predictive maintenance, identify failure, and suggest resolution paths. We wanted to show you that when that is done, we are also capable of doing the planning and the orchestration and the execution all together. There are two takeaways that you need to keep in your mind. Takeaway number one, as you have seen, we have had many people involved in this experience. We did not send any emails. All of it was through task allocation, task completion, so everything is digitally continuous. Why is that important? It's important for two reasons. Reason number one is because it's efficient. Email is the worst tool when it comes to efficiency. Reason number two is it's important because it creates a digital track. And that digital track by itself, of course, provides traceability, but it provides additional data so that we can learn and continue to enhance our enterprise knowledge and know-how and improve the accuracy of our system. So that's takeaway number one, digital continuity. Takeaway number two, you have seen it several times. We told you a lot about the virtual world and the real world. I did show you today how we are using the virtual world to do simulation to generate data that we then use for computing our predictive maintenance. You did see here how we are using 3D virtual world to deliver work instruction to the agent. And everything we do, you will see, is always the right combination of the virtual and the real, the virtual extending and improving the real world. And that creates unique new opportunities for manufacturing industry. Thank you very much.